Good day, esteemed researchers and viewers worldwide. We're excited to present DMOFC, Discrimination Metric Optimized Feature Compression by Chongsheng Gao, Ying Zhang, Li, Dong Lu, and Feng Wu. This groundbreaking research delves into the critical role of feature discriminability in machine vision tasks and introduces an innovative metric to preserve this discriminability during compression. Stay tuned as we unravel the intriguing trade-offs and insights the study offers. In this slide, we delve into the key highlights of our research. The primary motivation behind our work is the significant role of feature discriminability in machine vision tasks. We underscore the need to preserve this discriminability during the compression process, which is often overlooked in existing methods. Addressing this issue, our research focuses on maintaining the discriminability of original features during compression. We tackle the challenge of preserving this crucial aspect, which is often compromised in current approaches. In essence, our work is a pioneering effort to emphasize the importance of inter-feature relationships in feature compression, particularly in the context of feature discriminability. We hope that our findings will pave the way for more efficient and effective feature compression techniques in the future. Moving on to our key highlights. Firstly, we underline the importance of feature discriminability in machine vision tasks. This is crucial because maintaining the distance between features of different categories helps preserve their discriminability. Secondly, we demonstrate that our proposed discrimination metric can effectively preserve this discriminability. This metric, which includes an anchor, a positive and a negative, enhances the discriminability between different categories. Lastly, we reveal a trade-off between the discriminability of original features and our proposed discrimination metric. This trade-off is an important consideration in our work, as it influences the effectiveness of feature compression. In the future, we plan to extend this metric to more machine vision tasks and explore other inter-feature relationships for more feature compression techniques. Stay tuned as we delve deeper into these insights. In this slide, we're going to highlight the key contributions of our research. Firstly, we've introduced a novel discrimination metric. This metric is designed to preserve the discriminability of original features during compression. This is crucial in machine vision tasks, where feature discriminability can significantly impact the performance of the system. Secondly, we've proposed a method that involves the extraction of the original feature and an optimization strategy. This method is particularly useful in feature compression, where it's important to maintain the quality of the compressed features. These contributions not only enhance the performance of machine vision tasks, but also open up new avenues for future research in feature compression techniques. Stay tuned as we delve deeper into these concepts in the following slides. In this slide, we delve into the key highlights of our research. The main idea revolves around the introduction of a novel discrimination metric for feature compression in machine vision tasks. This metric is designed with a specific goal in mind: to preserve the discriminability of original features. Our method involves a multi-step process. We start by analyzing and comparing the quality assessment of image and feature compression. This gives us a solid foundation to introduce our proposed discrimination metric. Next, we present a specific feature compression method that leverages this metric. We then discuss the extraction of the original feature and our optimization strategy. This comprehensive approach ensures that we maintain the discriminability of original features, which is crucial for effective machine vision tasks. In essence, our research is a pioneering effort to address the importance of inter-feature relationships in feature compression, particularly in the context of feature discriminability. This work has significant implications for tasks such as person re-identification and face verification. Moving on to our key highlights. First, our proposed discrimination metric has proven to be effective. We compared it with the similarity metric and found that it significantly enhances the discriminability of features in machine vision tasks. Second, we discovered a trade-off between the discriminability of original features and our proposed discrimination metric. This means that while our metric improves the discriminability, it also needs to balance with the original feature's discriminability. Lastly, we found that with enough information capacity, the similarity metric can also preserve the compactness and discriminability of the original features. This is particularly true at high information capacities, where the similarity metric even outperforms the discrimination metric. These findings provide a new perspective on feature compression in machine vision tasks, and we believe they will pave the way for more efficient and effective machine vision systems. Thank you. Moving forward, let's take a look at this figure on the left. It illustrates our proposed discrimination metric and compares it with the similarity metric. You can see visualizations of original and reconstructed features optimized by both metrics. This brings us to the problem we're addressing in this paper: feature discriminability in machine vision tasks. Our focus is on the importance of feature discriminability. Why is this significant? Well, when we compress features, it's crucial that we preserve their discriminability. This is because discriminability is the basis of classification, which plays a key role in various machine vision tasks. So, in essence, we're looking at how to maintain the unique characteristics of these features during compression, which is a significant challenge in the field. On this slide, we have an illustration of our proposed discrimination metric, which we've compared with the similarity metric. This comparison includes visualizations of both original and reconstructed features optimized by both metrics. Now, let's delve into some issues with existing approaches. Firstly, these methods may struggle to find the correct gallery image for a query image, particularly when working with lower information capacities. Secondly, the compactness of features extracted from a specific identity may not be as good with existing metrics. Lastly, the discriminability between different identities may not be well preserved. These issues highlight the need for our proposed discrimination metric, which aims to address these challenges and improve the performance of machine vision tasks. In the next slides, we will discuss how we tackled these issues and the results we achieved. On your left, you see an illustration of our proposed discrimination metric. This metric is designed to preserve the discriminability of original features during compression, which is crucial in machine vision tasks. It's compared here with the similarity metric, and you can see visualizations of original and reconstructed features optimized by both metrics. Now let's talk about our proposed solution. We've introduced a new discrimination metric. This isn't just a theoretical concept. We've developed a method that involves the extraction of the original feature and an optimization strategy. This approach allows us to maintain the distinctiveness of the original features even when they are compressed. In essence, we're not just preserving information. We're preserving the right information, the kind that allows us to distinguish between different identities or objects in machine vision tasks. This is a significant step forward in feature compression techniques, and we're excited to share more about it with you. On this slide, we delve into the heart of our research, the proposed discrimination metric. As you can see in the figure on the right, we've illustrated how this metric compares to the similarity metric. The visualizations show both original and reconstructed features optimized by both metrics. Now, let's talk about how we evaluated our method. We compared it with the similarity metric to gauge its effectiveness. This comparison allowed us to understand how well our discrimination metric preserves the discriminability of original features during compression. Moreover, we didn't stop at just comparing metrics. We also examined the reconstructed features to further assess the effectiveness of our method. By doing so, we could observe how the features behaved after being processed by our method. In essence, our research is not just about proposing a new metric, but also about ensuring its effectiveness and utility in real-world applications. We believe that our findings will contribute significantly to the field of machine vision tasks and feature compression techniques. Begin a frame title, a method in feature analysis. Begin a mini page, T as 0.5 line width. Begin a figure, centering, include graphics, height equals 0.8 text height, SRC task underscore execution extracted underscore paper underscore data, 2405.04044v1, figures, 2405.04044v1 figure 3:1.png, end of figure, end a mini page, hfill, begin a mini page, T as 0.5 line width, begin itemize, item figure. Visual representation of reconstructed features in a two-dimensional space using tsni. The markers times and represent query and gallery images respectively. Item key insight. The paper demonstrates the effectiveness of the proposed discrimination metric in preserving the discriminability of original features during compression, especially in tasks like person read. It also highlights the importance of sufficient information capacity in maintaining feature compactness and discriminability. end itemize, end mini page, end frame. Begin frame. Frame title our related works. Begin itemize. Item let's delve into the related works. Item we've explored the quality assessment of image and feature compression, a crucial aspect in machine vision tasks. Item we've also introduced the similarity metric, a common method used in feature compression. Item however, we found that it doesn't always preserve the discriminability of original features during compression. Item to address this, we proposed a new discrimination metric, which we've compared with the similarity metric. Item our findings show that the discrimination metric effectively preserves the discriminability of original features, a significant improvement over the similarity metric. End itemize, end frame, begin frame, frame title our approach, begin itemize, item feature compression and analysis, begin itemize, item we employ a simple feature compression method using two fully connected layers, acting as the encoder and decoder. Item we analyze our method by visualizing the reconstructed features in a two-dimensional space. Using t-SNE, item we assess the impact of the discrimination metric by varying the information capacity constraints. End itemize, item performance evaluation, begin itemize, item for lower information capacities, more query images fail to find their corresponding gallery images, item for higher information capacities. Our method achieves higher compactness and discriminability than existing approaches. Item we demonstrate that with sufficient information capacity, a similarity metric can preserve the original features' compactness and discriminability. End itemize, end frame, begin frame, frame title feature analysis and compression, begin itemize, item feature analysis, begin itemize, item the proposed method is analyzed by examining the reconstructed features, visualized in a two-dimensional space. Item the compactness and discriminability of features are compared under different information capacities. Item with sufficient information capacity. A similarity metric can preserve the compactness and discriminability of the original features. End itemize, item feature compression, begin itemize. Item features are represented as 1D vectors and compressed using two fully connected layers. Item the impact of the discrimination metric is assessed by varying the information capacity constraints. End itemize, end frame, begin frame, frame title our related works, begin itemize, item limitations of baseline approaches, begin itemize, item networks optimized for minimizing cross, entropy and triplet loss can produce features with lower and higher discriminability, respectively. This means that while these networks are effective in their own right, they may not always yield the best results in terms of feature discriminability. Item the performance of these networks is lower than that of the proposed method, especially at high information capacities. This suggests that our method is more efficient and effective, particularly when dealing with large amounts of data. Item the discriminability of the original features extracted from these networks is not well preserved during compression. This is a significant drawback, as it means that important information may be lost during the compression process. End itemize, end frame, begin frame, frame title discrimination metric and its mechanism, begin mini page, t 0.5 line width, begin itemize, item figure. Mechanism of the proposed discrimination metric and its role in preserving feature discriminability. Item understanding the discrimination metric, begin itemize. Item the discrimination metric is designed to maintain the inner distance between features of different categories, enhancing their discriminability. Item it involves three samples, an anchor, a positive, and a negative. The anchor and positive belong to the same category, while the negative belongs to a different one. Item the metric is computed to ensure the positive is close to the anchor and the negative is distant, thus preserving the discriminability of features. End itemize, end mini page, hfill, begin a mini page, t a 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, src task underscore execution, extracted underscore paper underscore data, 2405.04044v1, figures, Figures, 2405.04044v1 figure 1-to-1.png. Caption illustration of the discrimination metric mechanism. The distance of features from different classes is constrained to be larger than the distance of features from the same class. End of figure, end of mini page, end of frame, backquote, begin a frame, frame title a discrimination metric and its application, begin mini page, T 0.5 line width, begin itemize, item figure. The mechanism of the discrimination metric and its application in feature compression. Item understanding the discrimination metric, begin itemize. Item the discrimination metric is designed to enhance the discriminability between different categories. Item it operates by maintaining the interdistance between features of different categories, using three samples, an anchor, a positive, and a negative. Item the metric is computed using a distance measure and a margin that defines the minimum difference between the distances. End itemize. Item application of the discrimination metric, begin itemize. Item the discrimination metric is applied to a few features in each optimization iteration. Item it helps to preserve the discriminability of all features in the training set. Item the metric alleviates the phenomenon of overlap, which is a common issue with the similarity metric. End itemize, end a mini page, hfill, begin a mini page, T as 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, a src task underscore execution, extracted underscore paper underscore data, 2405.04044v1, figures, 2405.04044v1 figure 1-to-1.png, captiona, the mechanism of the discrimination metric and its application in feature compression. End of figure, end of mini page, end of frame, backquote. On this slide, we have an illustration of the proposed discrimination metric and its comparison with the similarity metric. This visualization includes both original features and reconstructed features optimized by both metrics. Our approach to the problem begins with an analysis and comparison of the quality assessment of image and feature compression. This allows us to understand the trade-offs involved in different compression techniques. Next, we introduce our proposed discrimination metric. This metric is designed to preserve the discriminability of original features during compression, which is crucial for machine vision tasks. We then present a specific feature compression method. This method involves the extraction of the original feature and an optimization strategy. The goal here is to ensure that the compressed features retain as much of the original information as possible, while also being efficient to store and process. In essence, our research is about finding the balance between preserving the discriminability of features and the efficiency of compression. This balance is key to improving the performance of machine vision tasks. Backquote, begin a frame title a discrimination metric and its application, begin mini page, T 0.5 line width, begin itemize, item figure, an illustration of how the discrimination metric works in practice. It shows the mechanism of maintaining interclass distance to enhance discriminability. Item application of the discrimination metric, begin itemize. Item the discrimination metric is applied iteratively to all features in the training set, preserving their discriminability. Item this metric is particularly effective in preventing overlap, a common issue with the similarity metric. End itemize, end a mini page, hfill, begin mini page, T a 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, src task underscore execution, extracted underscore paper underscore data, 2405.04044v1, figures, 2405.04044v1 figure 1-to-1.png, end of figure, end a mini page, end a frame, backquote. On this slide, we delve into the technical details of our research. The figure on the left illustrates our proposed discrimination metric and how it compares with the similarity metric. It provides a visualization of original features and reconstructed features optimized by both metrics. Now, let's talk about our experimental design. We conducted experiments on the person read task using different metrics. We trained the machine vision network with these metrics to acquire original features with varying levels of discriminability. These features were then used to train the compression network. and we evaluated their performance. In essence, our research is about understanding and preserving the discriminability of features in machine vision tasks, and this slide gives you a glimpse into the technical aspects of our work. On this slide, we have an illustration of our proposed discrimination metric, which we've compared with the similarity metric. The figure shows a visualization of original features and reconstructed features optimized by both metrics. Now, let's delve into the technical improvements we've made. Firstly, we found our proposed discrimination metric to be effective when compared with the similarity metric. This is a significant step forward in our research. Secondly, we've identified a trade-off between the discriminability of original features and our proposed discrimination metric. This balance is crucial to understand for optimal feature compression. Lastly, we discovered that with enough information capacity, a similarity metric can also preserve the compactness and discriminability of the original features. This finding opens up new possibilities for feature compression techniques. These technical improvements are paving the way for more advanced machine vision tasks. Stay tuned as we delve deeper into our research in the coming slides. On this slide, we delve into the technical results of our research. As you can see in the figure, we have compared the evaluation performance on different metrics. The two key metrics we focused on were sim-feat and dis-feat. Our key finding here is the effectiveness of the proposed discrimination metric. We found that this metric, when compared with the similarity metric, proved to be quite effective. This is a significant result as it helps in preserving the discriminability of original features during compression, which is crucial for machine vision tasks. In simpler terms, this means that our proposed metric can help in maintaining the distinctiveness of features even when they are compressed, which is a significant advancement in the field. We'll continue to explore these results and their implications in the following slides. Stay tuned for more insights into our research. On this slide, we delve into our technical results, specifically focusing on the trade-off between discriminability and our proposed metric. As you can see in the figure, we have compared the evaluation performance on different metrics. The two sub-figures represent the performance on sim-feat and dis-feat respectively. Our key finding here is that there is a significant trade-off between the discriminability of original features and the proposed discrimination metric. This means that as we strive to preserve the discriminability of original features during compression, we also need to balance it with the effectiveness of our proposed discrimination metric. This trade-off is crucial in our study as it guides us in optimizing our feature compression techniques. It's a delicate balance, but one that can lead to more efficient and effective machine vision tasks. In the next slides, we will further explore this trade-off and discuss its implications in more detail. Stay tuned. On this slide, we delve into our key results, focusing on the visualization of reconstructed features. We used a technique called T-SNE to map these features into a two-dimensional space, specifically for the person read task. The figure you see here compares the evaluation performance on different metrics. The first part, labeled as A, shows the performance on sim-feat, while the second part, labeled as B, displays the performance on dis-feat. This visualization allows us to better understand the behavior of our proposed method and how it performs in comparison to other metrics. It's a crucial step in our analysis, helping us to refine our approach and improve its effectiveness. Let's now delve into our technical results. As you can see in the figure, we have a comparison of evaluation performance on different metrics. The first part, labeled as A, shows the performance on sim-feat, while the second part, labeled as B, shows the performance on dis-feat. Our key finding here is the significant role of sufficient information capacity. We discovered that when there is enough information capacity, a similarity metric can effectively maintain the compactness and discriminability of the original features. This is achieved by maximizing signal fidelity. In simpler terms, with enough information, we can preserve the unique and distinguishing characteristics of the original features, making them easier to identify and differentiate. This is a crucial aspect in machine vision tasks and feature compression techniques. Moving on to our technical results, let's take a look at this figure. It compares the evaluation performance on different metrics. On the left, we have the performance on sim-feat, and on the right, we have the performance on dis-feat. Now, let's delve into some ablation studies and their implications. One of the key aspects we focused on was the influence of discriminability on performance. Discriminability, in this context, refers to the ability of our system to distinguish between different features. We found that the discriminability of original features plays a significant role in machine vision performance. In simpler terms, the better our system can differentiate between features, the better it performs. This is a crucial insight that can guide future research and development in machine vision tasks. Stay tuned as we continue to explore these fascinating findings. On this slide, we delve into our technical results. As you can see in the figure, we have a comparison of evaluation performance on different metrics. The two graphs represent the performance on SimFeat and DisFeat respectively. Now let's talk about SimFeat and DisFeat. These are two types of features that we extracted from the fast-read network. SimFeat was optimized with only cross-entropy loss, while DisFeat was optimized with only triplet loss. These ablation studies and their implications are crucial to our research. They help us understand the impact of different optimization strategies on the extraction of features. This, in turn, influences the discriminability of original features during compression, a key focus of our study. In the next slides, we will further explore the implications of these results. Stay tuned. On this slide, we delve into the technical results of our study. As you can see in the figure, we have compared the evaluation performance on different metrics. The two sub-figures represent the performance on SimFeat and DisFeat respectively. Now, let's focus on the ablation studies and their implications. We found that the performance of discrimination metrics with SimFeat was particularly noteworthy. SimFeat, which has lower discriminability, surprisingly showed that discrimination metrics perform better with features of lower discriminability. In simpler terms, this means that our proposed discrimination metrics are more effective when the features are less distinguishable. This counterintuitive finding opens up new avenues for further research and optimization in feature compression techniques. Remember, the goal here is to preserve the discriminability of original features during compression, and these results provide valuable insights towards achieving that goal. On this slide, we delve into the technical results of our study. As you can see in the figure, we have compared the evaluation performance on different metrics. The two graphs represent the performance on SimFeat and DisFeat respectively. Now, let's talk about our ablation studies and their implications. We applied discrimination metrics to DisFeat, which is known for its high discriminability but lower compactness. Interestingly, we found that DisFeat showed lower performance when these metrics were applied. This finding is significant as it highlights that the optimal trade-off point is not constant, but rather, it depends on the discriminability of the original features. This insight can guide us in future research to better understand and optimize the balance between discriminability and compactness in feature compression. Stay tuned as we delve deeper into these findings in the next slides. In our research, we've placed a strong emphasis on the importance of feature discriminability in machine vision tasks. We've found that it's crucial to maintain this discriminability during the compression process. This is because discriminability is a key characteristic of features, forming the basis of classification in various machine vision tasks. To address this, we've introduced a novel discrimination metric. This metric is designed to preserve the discriminability of original features during compression. By comparing it with the similarity metric, we've been able to verify its effectiveness. This approach allows us to maintain the essential characteristics of the original features, even as they are compressed for efficient storage and transmission. In conclusion, our work highlights the need for a more nuanced approach to feature compression, one that takes into account the inter-feature relationships and the discriminability of features. We believe that this approach can significantly improve the efficiency and effectiveness of machine vision tasks. In this slide, we delve into our key findings and observations. Firstly, we have successfully verified the effectiveness of our proposed discrimination metric. We compared it with the similarity metric, and the results affirm its utility in feature compression tasks. Secondly, we've discovered a crucial balance that needs to be struck. There's a trade-off between the discriminability of original features and the proposed discrimination metric. This balance is vital during the compression process. In essence, our research has opened up new avenues in machine vision tasks. Particularly in feature compression, we've introduced a metric that not only preserves the discriminability of original features, but also maintains a balance during compression. This balance is the key to achieving high performance in both low and high information capacities. In our concluding remarks, we've observed two key points. Firstly, the performance improvement is directly linked to the discriminability of the original features. Our experiments have shown that when the discriminability of the original features is lower, we see a higher performance improvement. This highlights the importance of feature discriminability in machine vision tasks. Secondly, we found that with sufficient information capacity, the preservation of compactness and discriminability is possible. Interestingly, a similarity metric can also preserve these features, provided there is enough information capacity. This demonstrates that maximizing signal fidelity can maintain the compactness and discriminability of the original features. These findings open up new avenues for future research, particularly in extending the discrimination metric to more machine vision tasks and exploring other inter-feature relationships for more feature compression techniques. Thank you. In conclusion, we have some exciting directions for future work. We aim to extend the discrimination metric, which has proven effective in preserving feature discriminability during compression, to a wider range of machine vision tasks. This will allow us to further test and validate its effectiveness across different scenarios and applications. In addition, we plan to delve deeper into the exploration of other inter-feature relationships. This will enable us to develop more sophisticated feature compression techniques, potentially leading to even better performance in machine vision tasks. In essence, our goal is to continue pushing the boundaries of what's possible in machine vision, and we believe these future steps will bring us closer to that goal. Thank you for your attention, and we look forward to sharing our future findings with you.